Today's lesson is over 6.1 and 6.2, an introduction to probability and principles of probability. Before we get started on examples, I just want to cover some vocabulary that's going to be important for understanding things during this chapter. The first thing we're going to talk about is an experiment, and that just means a situation that has several possibilities. Okay, this may be rolling a die or flipping a coin. Okay, then the outcomes are just the results of the experiment then. So if I'm rolling a die, the outcomes would be getting a 1 or getting a 2, and so on. Now the sample space is the set of all possible outcomes. So if we talk about that rolling a die there, we've got 1, 2, 3, all the way up to 6 possible outcomes for the event. And notice it says the set of all possible, so we want to make sure that we put that in set notation. Now, an event is any subset of the sample space of an experiment. So for our set above here, we could talk about, instead of rolling a dice in general, we could talk about the event of rolling an even number. Okay, so that subset would look like 2, 4, or 6. All of those would be outcomes of that event. Okay, when I talk about probability of event, that's just any number from 0 to 1, and if you notice, it's denoted P of X. That just stands for probability of an event there. Okay, and it's between 0 and 1 with both 0 and 1 included. Now this 0 means that the event had no chance of happening or it was impossible. The 1 would mean it absolutely had to happen. There was a 100% chance of the event occurring. Now, this number between 0 and 1 is just going to measure the likelihood of an event of occurring. Another way we can represent this is as a fraction. The probability is going to be equal to the number of favorable outcomes over the total number of outcomes. Okay, so let's talk, for example, the probability of getting a heads when we're flipping a single coin. Okay, the number of favorable outcomes, that's the heads. Okay, so there's only one outcome when I flip a coin, heads or tails, and the only favorable one is getting a head, so that's 1. Now the total number of outcomes would be 2 because I could get a heads or a tails there. So the probability of getting a heads is 1/2. Okay, and this leads kind of to our next term, which is fair or unbiased. That's just an experiment in which all outcomes of the sample space are equally likely. Okay, so we talk about rolling a dice or flipping a coin. We hope that that's a fair experiment because it's equally likely to get a heads as it is a tails, or it's equally likely that we roll a 1 compared to rolling, say, a 4. The next vocab on our list here is randomly or at random. That's just a way of sampling a population so that every member has an equal chance of being chosen. Okay, so if we were sampling, we could talk about drawing names out of a hat. Okay, if I draw one name out of a bunch of slip of papers in a hat, okay, each slip would have an equal chance. Okay, so that is an example of randomly selecting or randomly sampling. The last term that we need to talk about is the empty set or the null set, and you should be pretty familiar with this. It's just a set that has no elements, and two different notations for this. First of all, we can literally have a set with nothing in it, the empty set, or you've used this symbol a lot to represent the empty set as well. Okay, so if we take a look at our first example here, we've got 2 6-sided fair dice, and they're tossed each time the 2 numbers are recorded. Okay, so we're not rolling one after another, just both at the same time, and we're going to write those 2 numbers down. Okay, we want to list all the possible outcomes for this experiment. Well, since we have 2 dice, we have to talk about 2 different numbers that are going to appear on those dice. Okay, so if we look at the first number, we could have a 1 with a 1. Okay, well, we could have a 1 with a 2 then, a 1 with a 3, all the way up to a 1 with a 6. Okay, but we want to do that for each number, so let's suppose we have a 2 with a 1, a 2 with a 2, again all the way to 2 with a 6, and we're going to continue that process down for each row all the way till we get to the highest number of a dice, which is 6, 1, all the way down to 6, 6. What that looks like as a set is this dice chart, and we'll use this a lot working with problems in the chapter and working with the book examples. We have a list of all of the outcomes for this experiment. Okay, how many are there? Well, if there's 6 rows and 6 columns, that means there should be 6 times 6, 36 different outcomes in this sample space. Okay, again, any sample space, we want to make sure that we put it in set notation brackets around it. Okay, our second example, we have a box containing 30 blue, 30 green, and 25 red paper clips. And 2 paper clips are taken from the box and their colors are recorded. Again, they're taken at the same time, and we're just writing down their color. We're not necessarily writing down the order in which we get the color. Okay, so this is going to be important for listing the possible outcomes for the experiment. Okay, so looking at this, let's start out with picking on 2 blue paper clips. Okay, we didn't get any other colors, just blue. Okay, well we could also get a blue and a green, or we could get a blue and a red. Okay, so we've covered all the ones with blue there. Okay, well let's assume, looking at our next color, we get 2 greens. Okay, we want to group that with the other 2 colors. Green with blue, we've already covered here. Again, we're just writing down the color, not necessarily the order. Blue with a green would be the same thing as green with a blue, so we don't want to write that down twice. Okay, so we've grouped green with blue. We want to make sure we group green with red then. Then we've covered all of the green options. Last one here is red. We could get both red, and then we want to make sure that we've grouped red with blue, which we have, and grouped red with green, which we have again. So that is the complete list of the outcomes for that experiment. Okay, all we have to do for part B is just count them up. We've got 1, 2, 3, 4, 5, 6 different possible outcomes for this particular experiment. Okay, now example 3 is a little bit different because order is going to matter here. We've got a researcher studying a number of boys and girls in a family with 3 children here. So now we're picking on 3 at a time, but a girl and a boy would be different from boy, girl. Okay, order of the births do matter here. Okay, of course we're going to assume that the birth of a girl or a boy is equally likely, and that's going to help us with the probability on part B. But first we just want to list out the sample space. Okay, so let's start out assuming 3 children that they're all boys. Okay, so boy, boy, boy. Okay, so we've covered 3 boys. Let's talk about the options for 2 boys. Okay, if I have 2 boys, I could have boy, boy, girl. Okay, with the girl being the last child. I could have boy, girl being the middle child. Or I could have girl, boy, the girl being the first child. Okay, so that's all of the ones with 2 boys, and then we just have to talk about 1 boy. Well, I could have the boy be the firstborn, then girl, girl. I could have the boy be the middle child, girl, boy, girl. Or I could have the boy be the youngest child at the end. Okay, so I've covered 3 boys, I've covered 2 boys, 1 boy. Last thing is no boys. Suppose we have all girls in this family. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8 different outcomes here in our sample space. Okay, that's going to be helpful when we try to find the probability. Remember that probability of an event is the number of favorable outcomes over the total number of outcomes. So we want there's exactly 1 boy. That would be our favorable outcome here. Okay, so we just need to look above where we're dealing with just 1 boy. Okay, so we've got 3 here, 2 in all of these. There's one boy, there's one boy, and there's one boy. So there are 3 favorable outcomes in this experiment. And then we want the total number of outcomes, which we counted up was 8. So the probability of having exactly one boy would be 3/8. Now, before we get to the examples for 6-2, I just want to cover some information that will help us work through these problems. Okay, we're going to talk about the addition counting principle for mutually exclusive events. Now, first, we just want to talk about what it means to be mutually exclusive. Okay, these are events that have nothing in common. Okay, they would not overlap. Okay, so for example, we could talk about the number of cats and number of dogs. Okay, if I group those, there's not going to be any overlap because there won't be any cats that are also dogs. There won't be any dogs that are also cats. Okay, so these are mutually exclusive because they don't ever overlap. Okay, so some notation here. We've got 2 finite sets. Remember, finite just means we can count the number in there. A and B are mutually exclusive. Then, to find the number of A, remember this U means union B. So if we want to find the union of those 2 events, all we have to do is find the number in event A and add it to the number in event B. Okay, it works the same way for probability. Okay, the probability of the union is just going to be the probability of event A happening added to the probability of event B happening. Okay, this is different from when 2 events are not mutually exclusive. So there's some sort of overlap or some sort of intersection going on. Again, given 2 events, 2 finite sets, A and B, the number in the union is going to be equal to the number in the first event plus the number in the second event. But notice we have something else added on here. We're subtracting off A. Remember, the upside down U means intersect. We're subtracting off the intersect. Okay, this makes sense because if we're talking about, say, a group of 13 student athletes, and I tell you that out of that group we have 7 basketball players and 7 individuals who are out for track. Okay, let's call that 8. Okay, that couldn't be true if there's only 13 because 7 plus 8 we know is 15. Okay, the only way this is possible is if we have 2 students who are both basketball players and out for track. So there is an intersection. We don't want to count those people twice. Okay, so that's why we have to subtract off any intersection. So anybody who would be grouped in both basketball or both track for this particular situation. Again, it works the same way for probability. Okay, we've got probability of A or B. Notice this or, that's the same thing as change up here, the union. Union means or for us in words. Okay, it's going to be equal to the probability of A plus the probability of B, and then we just want to take off that probability that both happened because we don't want to count them twice. Okay, what this looks like in pictures, which we'll work with to solve some of these examples, we've got Venn diagrams that represent both mutually exclusive or events that overlapped. Okay, another word you might hear for mutually exclusive is disjoint. That just means separate from each other. Notice in your picture there is no overlap, there's no intersection. Okay, and if we look down here in symbols, we've got A intersect B is equal to the empty set. Well, there is no intersection, so it makes sense that it is the empty set there, or the null. Alright, so overlapping ones, they will have an intersection, and that, as you can see in symbols, we have the intersection not being the empty set. That just means that there has to be something going on there in the overlap. Okay, one more thing we need to talk about is the idea of a complement. Okay, so let's just look at a different experiments here. The first one, we've got tossing a coin. The sample space, remember, all possible outcomes. We've got heads or tails. And we want to pick on the event of getting a tails. Well, the complement is going to be everything that is not the event we picked on. So looking at our sample space, we don't want to include tails. The complement is just heads. Okay, well, let's check out if we have more than 2 outcomes in our sample space. We're going to toss 2 coins. Our sample space, we could get a heads with a heads. We could get a heads then a tails. We could get a tails then a heads, or a tails and a tails. So if we want to pick on the event of getting no heads or getting both tails, the complement would be everything except for that tails tails. So getting 1 heads or getting 2 heads, that heads heads, heads tails, or tails heads there. Last example here, we've got picking an integer from 1 to 100. The sample space just is all integers, okay, including 1 and 100. And we want to pick on the event of picking a prime number. Okay, the complement is going to be everything that is not prime. Okay, so picking the number 1 because that's not a prime number, or picking a composite number, composite just meaning a number that has factors other than 1. Okay, we can figure out a theorem here based off of the probability for complements. If A is the event that we're picking on just here, then the probability of not A, or the probability of the complement, is just going to be 1 minus P of A. Okay, this is true because the complement, by definition, is everything but. Okay, so we have to include the entire sample space, or the entire probability of 1, and just subtract off what we have for the probability of our given event. Okay, let's take a look at these examples now. We are given a dice chart to help us out with some of these problems. We've got 2 fair dice tossed. We want to know the probability of a sum of 7 or 11. Okay, this or for us, again, means union. So we have the probability of A would be the sum of 7, or the probability of B being the sum of 11. Okay, so what that looks like for us is we need to go find what sum of 7 looks like so that we can add the probabilities together. Okay, so looking at our chart over here, we're trying to look at 2 numbers that would add up to 7. So the first one I see here is this 6, 1. And our dice chart actually has a lot of symmetry. So if you look across this diagonal, all of those numbers have a sum of 7. Again, probability always looks like the number of favorable outcomes over the total outcomes. So we've got 1, 2, 3, 4, 5, 6 outcomes that gave us that sum we wanted. And then again, 6 by 6, there are 36 total outcomes here. Okay, so that's our probability for event A for the sum of 7. Okay, we also want to look at the sum of B, or the sum of 11 here. So looking at my chart here, none add up until 11 until right down here. Okay, and again, they're symmetrical, so we can follow the diagonal there. Okay, so there's only 2 favorable outcomes here, so it'll be 2 over that same 36. Okay, to decide what the union looks like, we have to just decide whether these 2 events are mutually exclusive. Looking at our numbers here that are underlined, we just want to make sure there's no overlap. Okay, if there's an overlap, we'll have intersecting events, but in this case, they don't touch each other. These are mutually exclusive, and mutually exclusive events, we just have to find probability of A and add it to the probability of B. That will give us the probability of the union. Okay, so we just take this 6 over 36 and add it to 2 over 36, which gives us 8 over 36. Okay, again, anytime we have a fraction that can be reduced, we want to make sure and do that. If we take a 4 out of both, we've got 2 9ths. So the probability of getting a sum of a 7 or a sum of an 11 when we roll 2 dice is going to be 2 9s. Okay, we'll do that same idea for this next one. We want to show doubles or a sum of 8. Okay, so event A would be rolling doubles, event B would be a sum of 8, and this or means union for us. Okay, or means union. All right, so let's go look for doubles on our chart here. Okay, again, it's kind of symmetrical. Doubles just mean we see the same number on both dice. Okay, so the probability of A is going to look like 6, that's the number of favorable outcomes, over the total of 36. Okay, looking at probability of B, we are looking for a sum of 8. Okay, so we just need to look for two numbers that add up to 8. We've got 6 and 2, 5 and 3. Again, we just want to go across that diagonal there, and we've got 1, 2, 3, 4, 5 favorable outcomes over 36 total outcomes. Now, looking at these ones here, we just want to look, is there an intersection? Okay, and that is true for this 4, 4. Notice that 4, 4 was included in the favorable events in Part A, and it was also included in the favorable events in Event B there. Okay, so what we want to do is be sure not to count it twice. So this we know, events of the union, probability of A union B is going to be equal to the probability of A plus the probability of B, but then we have to subtract off the intersection where they overlap. Missed my A there. Okay, so probability of that A intersect B. Okay, and in this case, the A intersect B was one event here. Okay, so that would look like 1 over 36. Okay, so probability of A was 6 over 36. We're adding that to probability of B, which was 5 over 36, and then we're subtracting off that intersection 1 over 36. Okay, in this case, we only had one outcome that was in both. There is always the possibility that we have more in our overlap, so be careful to pay attention to that. Okay, so we have 11 minus 1. That will look like 10 over 36. Again, every single time we can reduce, we want to make sure we do. So the probability of getting doubles or having a sum of 8 would be 5/18. Last problem on this example, we've got the probability that the dice show a product between 7 and 31. Now this is a single event, so all we're looking at is the probability of a product that is between, okay, so greater than 7 and less than 31. Okay, so if we look through here, let's talk about a product. If we multiply 1 times 1, we've got 1, then 2, 3, 4, 5. So far, we're not at that 7. 6 also is not included. Okay, so none of the top work for us. Okay, then we've got 2 there, 4, 6. Again, they don't work, but this one does work for us. This 4 times 2. That means 5 times 2, 6 times 2, we have a product that's greater. Okay, 1 times 3 doesn't work for us. 2 times 3 is 6, still not above 7. This one does. Okay, so we're good to go. Everything to the right of it should be a bigger product. Okay, we just have to make sure we do not go over 31, and we haven't with 6 times 3. Okay, 1 times 4 is not high enough, but 2 times 4 is. Okay, so we want to include that. And then looking to the right, just have to check and make sure this last one is not greater than 31, and it is not. Okay, so we're good to go there. 1 times 5 is 5. We don't want to pick on that one. 2 times 5, that works for us, so we want to include that. Again, moving this way, we've got 30, still works. 1 times 6 for us is 6. That does not work for between 7 and 31, but everything to the right here does up until this last one. 6 times 6 busts that 31, so we don't want to include that as well. So we've got a group of all of these being our favorable outcomes. We just need to add them all up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 favorable outcomes over our total of 36. Last thing, reduce that to 7/13. Okay, last example we're going to talk about, we have this situation where participants are going to a 2-day conference. Now, they can either choose to register for only one day, so only Friday or only Saturday, or they can register for both days and go both. Now, we know that there are 231 participants on Friday and 252 on Saturday. Another piece of information we're told is the total number registered is 350. Okay, but looking at our numbers for Friday and Saturday, if those were mutually exclusive, it would go over that 350. So we know that there have to be some people that attended both days. Okay, so there's going to be overlap. In order to figure out how many people belong in each group, we're going to make a Venn diagram. Okay, and again, we want there to be overlap because we know that there's some people who went both Friday and Saturday here. Okay, so looking at this, we know that the conference total was 350, but we know 231 and 252 people are accounted for. Okay, so if we look at that sum, we get 483. Okay, but we know that's not the real amount. There's really only 350. So if we subtract off that 350, we will find our intersection, that overlap that we got. Okay, so if we subtract those, we get 133. That's the amount of people who went both days. All right. Focusing on these numbers, we know Friday we had 231 participants. So this entire circle should count for 231. Okay, and looking at the other side, we know that this entire circle or oval here is going to count for 252. In order to find the participants who went Friday but not also Saturday, all we have to do is take the total value for Friday and subtract off that intersection. So we'll take 231 minus 133, which gives us 98 participants. Okay, doing that same thing for Saturday, we'll take 252 and subtract our intersection of 133. Okay, and that will give us 119 participants who just went Saturday. Every single time you draw one of these Venn diagrams, a good idea to make sure that you didn't count anyone twice is just add up those three numbers and make sure they give you the total that you were assigned or you needed there. And in this case, 98 plus 133 plus 119 is 350. Okay, so it does check out. All right, let's assume that we're drawing a name of a participant of the conference, okay, for a door prize. What is the probability that this person attended both days? So we're finding the probability of attending both days. Again, this is a single event, so we just have to find the total number of favorable outcomes, which the ones who attended both days was 133, and divide by the total number of outcomes, or the total number of participants, which is 350. Okay, last thing, reduce that. So we're looking at 19 over 50 for our probability that the person who got the door prize went to the conference both days. Okay, homework is on you. It's the last page of that packet you were given. If you have any questions, feel free to come ask.